So I want to talk about the notion of local to global principles in persistent homology. Local to global principles are, in fact, some would say that's actually all what topology is about. It's about starting out from local information and somehow integrating it all together and getting some global information. Could be argued that's what it's all about. But let me tell you, though, that it has a more specific meaning also in terms of techniques. And so I want to make the point, first of all, that computational topology relies heavily on direct computations from the definitions. So in other words, typically if we're computing persistent homology, the algorithms involved actually, do the linear algebra directly, with Gaussian elimination type algorithms. Standard topology doesn't have that option because standard topology, when you define the homology of a space, is defined to be singular homology, which at the very outset starts out with an uncountable dimensional vector space or uncountably generated abelian group. And so it's hopeless from the point of view of performing direct computations from the definitions. Can't be done. And so what the solution for standard topology has been, well, let me try to do some simple cases and then let me see if I can leverage them together, starting out kind of locally and building up globally. So the local to global principles are key. I would argue that injecting these local to global methods in computational topology and specifically persistent homology would result in parallelization and also better overall understanding of what we're doing. So in other words, that when we start dealing with these things, we can work with larger pieces of information at once and move them in a simplified way. So what do I mean by local to global principles? Well, the fundamental one is a so-called Meyer-Vittoris sequence. It tells you what happens when I have a space X given as a union of two subspaces Y and Z. And it takes this form. So you can see you need to understand not only the homology of the two subspaces, but the homology of the overlap. Okay. So that is, an interesting something that one can ask about. It really does say local to global because you've got two local pieces that are being assembled into a global piece. It can come from a covering with more than two sets. In this case, the output is no longer a long exact sequence, but it's instead a somewhat more complicated object called a spectral sequence. And a somewhat less deterministic object also in the sense that there's more homomorphisms that need to be computed. So in the long exact sequence for homology, you need to compute a single connecting homomorphism. Here in the spectral sequences, you compute families of differentials and so forth. Nevertheless, it's a fundamentally useful tool on the pure math side, pure topology side. So I would also call this a local to global principle. It says that a certain spectral sequence converges to the homology of the whole space. Another way to decompose space is as the product of two or more spaces. So as we said here, we have a kind of a union. If I instead take a product, question is, can one describe the homology of a product in terms of the homology of the factors? And it turns out that in regular topology, the answer is yes. Certainly with field coefficients, the answer has a very simple form in terms of the tensor product of the graded vector spaces of homology with field coefficients. And so when you don't have the field coefficients, when you just take integer homology, it's a little more complicated. There's a short exact sequence here which is actually split. And so there is actually an answer as well. It does involve you in, though, the computation of something slightly more exotic than we might be used to, which is derived functors of tensor product called Tor. Nevertheless, sort of complete answers in this setting as well. So what I would say is that both of these are examples of indirect methods. That is to say, they are methods that say, let me break up a space in some way or other. I understand the component pieces, and now let me assemble it together. That's as opposed to taking the whole thing brute force head on and computing. Okay. So here's an initial question. Let's think about this. Suppose that I have a metric space, and it's built up as a union of two subspaces, two submetric spaces. Okay. Can I somehow compute the persistent homology of X from the persistent homology of Y, the persistent homology of Z, and perhaps the persistent homology of Y intersects Z? Question is, can we do that? And let me say that the answer is clearly no in general. Because let's think about it. If we have restricted to these three subsets, we can easily check that there are different metrics on all of X that restrict to the same metric on Y, on Z, and on Y intersects Z. So, in other words, we're computing this from something which could come from many different metrics on X. And so it doesn't really, the question as posed, doesn't have a good answer. Okay, but let's step back then and say the following. Turns out that there is, if I'm given metrics on Y and Z, which restrict to the same metric on Y intersects Z, then there is a maximal metric on X which restricts to those two metrics on Y and Z. So that problem does have a solution, that is to say that I can choose, if I force my metric to be the one that is coming out of this Y and Z situation, then I do have a unique metric. And so one could say then, one could view X, that metric, as the push out of Y and Z and this over Y intersects. Okay, what is it I'm hitting here? Maybe I'm going to move this back. Try that. So you can view it as a push-out of metric spaces of this diagram right here. And one might then hope, so there is possibility for an answer that says, well, I'm going to be able to compute the persistent homology of Y and Z, I should say of X, with the metric given by the push-out metric for along YZ and Y intersects Z. One might hope. Don't have an answer to that question. But the question is, so what should we expect? So again, here might be the hope. This is the thing that comes out that you would get, and it would be again, it would be computing the persistent homology of X with that push-out metric. And this would be useful for a number of calculations, particularly for those with tree metrics. And that's an example that I'm going to talk about here in a minute. Okay, so I want to talk a little bit then about the technical ingredients to a theorem that I'm going to show you. Okay, a theorem along these lines that says that in a specific situation, in some specific situations, this in fact does hold. Okay. So simplicial complexes are defined as usual. Abstract simplicial complexes, a list of vertices and a collection of simplices. Sigma is a set of simplices. That's something standard everybody in the room is familiar with, I'm sure. Now, in a simplicial complex, suppose that I have a maximal simplex, okay, tau. So it's not contained as the face of any other simplex. And I have a subface of that, I have a codimension one face of that, which has the property that it is not a codimension one face of, or it's not a face of any other simplex, any other bigger simplex than tau. Okay, so in that case, once we have that situation, because sigma is not contained in any other simplex, I can actually freely remove both the maximal simplex and sigma and get a subcomplex. And it turns out that the inclusion of that subcomplex is a deformation and retract of the original complex. Okay? So we'll refer to that as the end point of the collapse. So the picture here is like this. You can see you've got on the left there, you've got sigma as a codimension one face of tau, And in this situation, sigma is not a face of anything else, so I'm free to remove both of them and get the thing picture on the right there. And those two have the same homotopy type. Okay. Now, given a finite metric space, we'll recall that the Vittoris-Rips complex, which is used to compute persistent homology, is defined as follows. So suppose that I need to define the simplices. The vertex set, first of all, is the set of points in the metric space X. And now we declare that a k+1 tuple of points spans a k-simplex if and only if the distance of xi and xj is less than or equal to r. So this is for a threshold r. Okay, so we'll denote that by Vittoris-Rips of x and r. Now, as you know, the first thing you always do when you talk about persistent homology is you recognize that when r is less than r prime, there's a natural inclusion of the complex with threshold r into the complex threshold r prime. And so we'll write Vr of x dash as, which is all these thresholds together, is a persistence object in the category of simplicial complexes. That is to say, it's a family of subcomplexes parameterized by r in such a way that it's increasing as the parameter r increases. Okay. So this Vittoris-Rips then for a finite metric space is a filtered simplicial complex. It means a simplicial complex with an r plus valued, so a non-negative real valued function on the simplices. So each simplex is given a filtration, and that filtration is the maximum distance between any pair of points within the simplex. So we get these subcomplexes here that I just described, and a filtered collapse of a filtered simplicial complex is a collapse of the total complex, but that has the property that rho of sigma is equal to rho of tau. In other words, they have the same filtration. So in this picture before here, the requirement here goes beyond just the fact that sigma is a codimension one face of tau and it's not a face of anything else. It also has to be the case that the filtration on the two is the same. And when you do that, then what you can say is, if you have a filtered collapse like that, you can say that the subcomplex, which is the endpoint of that collapse, has persistent homology isomorphic to the persistent homology of the bigger thing. Okay? And so again, here this is what happens at r equals 5. So in this case, I'm assuming that the red simplex and also the vertical line have the same filtration. And let me note. So this is r equals 5, but at r equals 3, those two might be actually identical. So when I'm talking about a collapse here, it might mean that it's a trivial kind of identity collapse at some filtration level, and at other filtration levels, it's an honest-to-God collapse. Yeah. And proof here, I won't run through the proof. Okay, so this technical result turns out to be applicable to the case of Meyer-Vittoris for Vittoris-Rips complexes. So under certain conditions, we'll be able to show that the Vittoris-Rips complex of the finite metric space is equivalent to a push-out of Vittoris-Rips complexes of subspaces. And the push-out is in the category of filtered simplicial complexes. Okay, it's a perfectly good category from that point of view. It does have nice notions of push-outs. And so the theorem makes sense. So let's do this. Let's now assume that I have a finite metric space X, and I have 2 points, x0 and x1, inside X. Let me define Vr of X and then x0, x1, and R. Let's have that denote the subcomplex consisting of all the simplices which don't contain both x0 and x1. So they're going to fail to contain one of them. They won't contain them both. Notice that subcomplex is a union of two things. One which would be the Vittoris-Rips of x minus x0, and the other would be Vittoris-Rips of x minus x1. And the two overlap then in something even smaller. So this complex that we've written down, that I've described here, is in fact a union of two chunks. Okay, so now here's the theorem. Suppose that x and x0 and x1 is in the previous slide. And also, suppose that the cardinality of x is 3 or bigger. So in other words, it doesn't just consist of x0 and x1. So it means that the intersection is non-empty. And suppose also that these 2 points, x0 and x1, have the property that they maximize the distance function. So they are 2 points that are maximally far apart within the space, within the metric space. Then the statement that is that this Vittorius Rips of x, x0 and x1, this thing which is a union of 2 things, maps into the Vittorius Rips of x itself and is a homotopy equivalence of filtered simplicial complexes, so it induces isomorphism and persistent homology. Okay, so in other words, in this situation, then I can actually get the Meyer-Vittorius sequence that we talked about for these 2 subsets. And the reason being that if I have a push-out of filtered complexes, then the persistent homology does obey the Meyer-Vittorius property. So here's the corollary. So in this case, when I'm removing these 2, when I'm taking these subsets which are very close to the whole thing, but nevertheless I get this persistent homology long exact sequence in that case. All right, so the question is, how do we do this? Why is this true? The strategy is to find a filtered collapse sequence. So I have a sequence of collapses starting with an initial one and then proceeding, performing one after another, all the while preserving persistent homology, because filtered collapses preserve persistent homology. Until I get down to this endpoint, which is the thing which is the union of the 2 pieces, Vittorius Rips of x minus x0 and Vittorius Rips of x minus x1. So what that means is I need to understand all the simplices in VR of x that are not in VR of x, x0 and x1. So I need to understand everything that's in the full Vittorius Rips that isn't in the subcomplex which is in the union. So it turns out that these simplices are in one-to-one correspondence with the subsets of x minus x0 and x1. Because what do they look like? The simplices, first of all, they contain x0 and x1. And so, because otherwise they would be part of the subcomplex. Okay? But now, since they've got x0 and x1 in them, the rest is determined by, well, what parts of x minus x0 and x1 are in there. And so, it's that subset. So it's characterized entirely by that. So there's 2 to the n of those, where n is the cardinality of x minus x0 and x1. Okay. So that's the correspondence. So there's a very simple understanding of that. Now, how do I build this collapse sequence? Well, first of all, I'm going to impose a total order on x minus x0 and x1. Just choose one. Using a lexicographic ordering, form the corresponding total ordering of the collection of all subsets of these. So there's a notion of a lexicographic ordering on subsets. And also that it has the property that it's consistent with the partial ordering determined by the cardinality. So I'm going to insist that larger cardinality subsets occur in this ordering before the smaller ones do, the smaller cardinality subsets. So the idea is I'm going to create a total ordering where I take the biggest set first, and now I have a way of choosing which one of the next down cardinality I choose, and I just work my way through. This is really a bookkeeping exercise, but now what we have is a total ordering of these simplices not in there. So we'll note that all the simplices corresponding to these subsets have filtration R. The reason they all have filtration R is they all contain x0 and x1, which is the biggest distance that occurred anywhere in x anyway. And so none of the distances that come from the other points are going to get bigger than that. So they all have the same filtration. Okay, so then what we do is we begin with the maximal simplex, and we select the maximal codimension 1 face in this ordering. This gives a filtered collapse, due to the fact that both the filtrations have the same filtration, and there's only one maximal simplex. So we remove these two things, and then we select the maximal remaining simplex in the ordering, and now we're going to choose its maximal codimension in one face, and I just work my way down. Okay. So just to give you a sense of it, the ordering looks like this when the cardinality of x minus x naught is 3. Okay, now, all right, so this is fine. This is not the way I usually like to proceed. If all I'm doing is sort of removing one point at a time, you know, I'm not getting smaller spaces that way very rapidly. But what I'm going to show you now is a result that came out of the work that I mentioned with the Rabodan group at Columbia, studying viral evolution. So the picture that you see here is a picture of the so-called tree of life. The notion that organisms form a tree, in some sense, goes way back. It goes back even before Darwin. Unfortunately, it's not always true. Okay, so the work that we found in that work that I mentioned with Rabodan and Chen was that when I do the following, when I take databases of viruses, so characterized by their sequences, and study them using a Hamming distance, and I ought to be getting a tree, I don't always get trees. Okay? I sometimes do, for some families, but others don't. And it turns out that the failure to be a tree is actually evidence of exotic forms of evolution, so-called non-clonal forms of evolution, where more genetic material is transferred than simply performing a single mutation. Okay. So, and what was surprising is that actually the persistent homology classes came in. When you write down the cycles that come out of the algorithm, they actually contain elements that show where in the sequence the exotic form of evolution occurred. That's pretty surprising. There's no a priori reason for that. In fact, the algorithm, we don't understand why it is that the persistence algorithm in this context should produce cycles that are relatively small. But in fact, that is what happens. Okay. So empirical observation, something that we've been thinking about. But the question, though, gets posed here. How do I determine whether something is tree-like or not? Okay. What I'm seeing is I'm seeing higher dimensional homology in some of these spaces. Well, maybe persistence homology creates that for trees. Who knows? Unless you prove something about the persistent homology of a tree-like metric space. So, tree-like metric space being one that, if I have a tree, perhaps a weighted tree with lengths on the edges, I have the metric that's given by counting or adding together the lengths of the edges in a minimal path. So that's a tree-like metric. Okay, so here's the theorem. And we kind of proved this with other methods before. Let T be a tree, and perhaps with these lengths assigned. Then it says that for any finite subspace T, the persistent homology vanishes for every I greater than 0. Okay. So it means there are no bars in higher degrees. So notice this is a somewhat different statement from what we might be used to. When we think about persistent homology, we're often thinking, oh, it's going to approximate the homology of some idealized space, a sphere or a torus or whatever it is. And so what we say is, yeah, it's going to have some long bars, and then it's going to have some short bars, though, because there's always noise in the system. We believe that we're going to see small bars. This is saying, no, for trees, there are no small bars, okay, in dimensions greater than 0. All you see is the zero-dimensional persistence barcode, and everything else is identically 0. Okay. Anyway, so here's a picture from that paper. So it said if we believe this theorem, then it says that this metric spaces coming out in several of these situations were not tree-like, and so there was evidence of non-clonal evolution. Okay. So here now let's talk about the tree. So given the weighted tree, the vertices of T form a finite metric space. What is the persistent homology of the metric space? Now let's note that T, of course, if T is a tree, it itself is by definition a simplicial complex, and in fact it's a persistent simplicial complex too, because what can I do as I add the threshold, increase the threshold, I'm going to include more and more edges. So initially it will be a zero-dimensional complex for the r equals 0, it'll just be the vertices. And then as I grow, it will increase. Now, that persistent complex embeds inside the Vitoris rips, which is much bigger. The Vitoris rips is not by itself a tree. It will, in fact, at the highest level of the parameter, it will be an enormous simplex, right? The simplex being the number of vertices in the tree. So there's a natural map, though, of filtered simplicial complexes like this, which takes T into the Vitoris rips on T. Because every edge here, when that edge gets included, those points will have distance, that pair of points will have distance less than or equal to that threshold, and so it will be included as a simplex in the Vitoris rips. Again, T is a one-dimensional simplicial complex with no loops, turns out. On the other hand, the thing on the right is some huge complex which has lots of cycles and so on in it. Okay. But suppose that I could prove that this map J here actually induces an isomorphism on persistent homology. Okay. Then I'd be done, because persistent homology of the thing on the left, because it's one-dimensional and has no loops in it, it's just going to be components merging into bigger components and so on. There are not going to be any loops, no higher dimensional homology. So the statement, instead of being a computational statement that says persistent homology vanishes, it's a space-level statement that says that for all practical purposes, T and Vitoris rips of T are the same thing, except for a lot of homotopy hair to it. Okay, so that's the theorem. So the theorem is that T is equivalent to Vitoris rips on T. So here's the corollary of the thing I was looking for. Okay. So let's notice that, of course, for simplicial complexes and even persistent ones, there's a notion of push-out. Okay. So let's do the following. Let's try to do an induction on the number of vertices in the tree. So let me notice that, of course, if I've got 2 vertices in my tree, then it's an easy calculation that T is actually isomorphic or homeomorphic to Vitoris rips on those 2 points, because there's just a single simplex and it appears at the same filtration level. So if I start out with a very small tree, that is to say a 2-point tree, I'm in good shape. You may ask, why don't I start with a tree with 1 vertex? Well, let me remind you that the excision theorem, which is what I'm going to try to use now, only applies in situations where I have at least 3 points. Okay? And so I can't go from 1 point to 2 points using my Vitoris. In fact, think about it, it actually fails at that point, because the push-out produces what's effectively an infinite filtration. Okay. So anyway, that's why I need to do an induction down to where there are only 2 points. Okay. All right. But so now the notion will be the following. I'm going to take my tree and I'm going to try to reduce the calculation to a tree of slightly smaller size. And so given a tree, we'll find a pair of points that maximizes the distance function on the tree. It's clear from the properties of trees that T0 and T1 have to be leaves of the tree. That is to say, they have to be out at the very tips. And so I'm going to let T0 equals T minus T1, T1 equals T minus T0. And so you can see here, I've got the 2 points. And I'm breaking into these 3 subtrees, each of which is smaller in terms of the number of vertices than the initial tree. So 2 of them are smaller by 1, and then the intersection is smaller by degree 2, or by 2 of them. So now we have a map of push-out diagrams that looks like this. So I got T0 intersected T1 and into T0 and T1. And I've got the same corresponding diagram for the Vittorius-Rips complexes here. So now the upper one here, if I create the pushouts, is by definition it's a pushout. The lower row turns out to be a pushout also because of the theorem that I just proved. And it said that Vittorius-Rips of T is actually equal to, or homotopy equivalent to, in a persistent sense, to the pushout of this diagram here. So this diagram right here has a VR of T and dash as its pushout. Now it's also a fact, just as in ordinary topology, that if I have a pushout diagram of this shape of persistent complexes, then and I have a map of diagrams, I should say I have two of these diagrams, and a corresponding map of pushouts, if the maps are equivalences on each piece of the diagram, so each of the two edges and also the thing in the middle, then the pushouts will be homotopy equivalent as well. Okay, so this is the basis for an induction. Okay. So now we might hope that one could take this a bit further. Okay. So, and an initial test case for us in trying to do this is to say, well, can we handle products of trees? What can we say about products of trees? And one's initial guess from looking at this might be that somehow the dimension pops up 1 with every product, as you'll see. But it turns out it's going to be much harder than that. So let me talk a little bit about products now, first of all. So products of metric spaces can be defined in various ways. For us, we're going to talk about the product of two spaces with the sum distance for the two. That will be what I want to talk about. And so the question is, now just like we asked before, can I compute the homology of a space in terms of being a union of things? Can I compute the homology of x cross y with this sum metric on any of these products in terms of the subpieces, ph star of x and ph star of y? So in general, what happens? In general, when you use generalized cohomology theories, you don't have a simple Künneth formula the way you do for ordinary homology. It takes the form, instead of a more complex object, one of these spectral sequences. Okay. But it applies when a generalized theory is a commutative ring valued. So G star of point is a ring, and I can actually talk about the Tor in this graded modules over that graded ring. So it turns out that the category of persistence modules is equivalent to the category of R plus graded modules over the ring K of R plus. So R plus here is the non-negative real numbers under addition. This is to be thought of as the ring of polynomials with real exponents of t, real exponents of t. This ring is actually bad in some ways. It's not Noetherian, which is an important property that gets used for many of the things that one works with. However, it turns out it does have a property that turns out to be just good enough, which is called coherence. So it is a coherent ring. And so what that means is that one can actually study, it turns out, the category of finitely presented modules. And in fact, they have barcode classifications. So this is where the barcodes come out, and it describes the precise relationship between the barcodes in this situation and the things that come out of the general Künneth formula over the integers or over polynomials. And it turns out here that finitely presented modules have a length 1 free resolutions. And also that Tor, the derived functors of tensor product, vanishes for I greater than or equal to 2 over this ring. Yeah?
So in terms of the spectral sequence, then what are the implications of that?
So the implications are then that the spectral sequence has only 2 lines, and that in fact the same thing that happens over the integers happens in this setting. So there's actually a split exact sequence in exactly the same way. So right there, yeah. Okay, so an R-filtered vector space is a total vector space with subspaces with this inclusion property. Now, if we're given 2 filtered simplicial sets, one can take the product of x and y, and you can equip it with this filtration like this R filtration. And the persistent homology of this, if I take a filtered, product of filtered simplicial sets, will have this kind of Künneth formula. It will work perfectly as you expect. So now consider the product of metric spaces with a sum metric, d of x plus d of y. We're going to use a simplicial set model of Vittoris-Rips. There's no problem with doing that. And the k-simplices are ordered k-tuples of elements in the metric space. And the filtration here of say, a simplex corresponding to x0 through xk is max over I and j of d of xi and xj. So it's the maximum distance that occurs among all these pairwise distances. So the underlying complex of VR, complex I should say, of VR x cross y is the product, and sorry about the typo there. So it looks like we should be in good shape. However, the filtration is different. So the filtration in the Vittoris-Rips complex is given by what's in row number 1 there, whereas the filtration in the product of the two filtered simplicial sets is max, the two maxes added together instead of the max of the sums. And those two are obviously different. But nevertheless, you could be a crazy optimist and say, well, but yes, it's small difference, it doesn't matter, maybe I believe that the Künneth formula is going to hold anyway. Maybe it holds up to homotopy or something. Okay, but before addressing that, there does turn out that there is a very natural map of filtered simplicial sets. The way it goes is it goes from the product of the Vittoris-Ripses into the Vittoris-Rips of the product. So that goes that way. So there is a map from this thing, which is which is computable by the Künneth formula, into the thing that we're studying. Okay? But it's not an isomorphism, and it turns out, unfortunately, alas, that's not even in general a homotopy equivalence of filtered simplicial sets. But when does it hold? Okay. So it holds, product of two metric spaces of cardinality 2. So, product of two lines, two graphs that are lines. In fact, it holds for a product of two trees. Okay. In fact, you can actually perform a proof that's very much like the one I just gave for trees, but that instead works for cubical complexes of dimension 2, where you map in and you can actually perform an induction very much like the one I just did to get an answer in that situation. It, however, does not work for a product of 3 trees. And in fact, you can see that it fails for, I2 cross I, but in general for an n-fold of products of copies of I, where n is 3 or bigger, when I is a 2-point metric space. So it fails, as I take the bigger products. Okay, so let's just look, why is this true? Well, the 1 cube is easy, all positive dimension barcodes vanish. So let's see, so 2 cube, when you compute, I cross I, what you find is this. You find that, of course, at filtration less than 1, you've got 4 points. At filtration between 1 and 2, you have the boundary of a box. So it's the boundary of a square. And then that gets then filled off when I go to filtration 2. It turns out that that thing that you described there actually is simple enough. It's very much consistent with our geometric intuition, and it is consistent with what comes out of the Künneth formula. Okay. Notice, though, remember that there was a one-dimensional class that occurred in there, right? Namely, that at the point between filtration 1 and 2, I've actually got the boundary of the square, and that's a loop. Okay, so that gets created, but I don't go beyond dimension 1. Okay, and that's in generic what happens for trees, products of 2 trees. That you actually get some classes in 0 and some classes in 1, and that's it. And you would think from that if I then take a product of 3 trees, I should get to dimension 2 and no bigger. Unfortunately, the 3 cube has a class in dimension 3, where if I had the intuition that I just mentioned, if that was correct, it would have a class in dimension 2. And you can actually go in and you can actually prove, and it's not very hard, that In fact, what happens in the general n cube is that there's a dimension of the complex, first of all, at threshold value n minus 1 in the n cube. That the dimension of the complex is 2 to the n minus 1 minus 1. Okay. And you can furthermore prove that there is a non-trivial integral cycle at that point. And so you see a single one sitting there at the top. So now what you have is you have you have a situation where you have persistent homology. You understand it at one high end, at the high end. You also understand it at the low end, where it's simply the zero-dimensional barcode for the cube, which is easy to write down. But then there's stuff in between, and actually it doesn't seem to show much of a pattern. Okay? It's at least not a pattern that I can discern. So I'm convinced that there's stuff to be found there, certainly. But, and I'm going to try to make a little guess about where it comes from. But at the moment, we don't understand what's going on in between. But in any case, the conjecture would be that still that for a product of n trees, one would expect that the dimension of the complex is still 2 to the n minus 1 minus 1. Again, conjecture out there, not a known fact. Okay, so, well, this is just the computation, which might not be of so much interest. Let's see. Okay. Yeah, so these intermediate dimensions are mysterious. So what I'd like to do is now to propose an approach to that. So the question is there some kind of souped-up Künneth formula in this setting? Okay. So what's clearly true is that Künneth is inadequate. It fails to be correct for even I cross I cross I, where I is an equal. Okay. So what I want to do is I want to replace R, or K of R, by a richer ring, a bigger ring. So actually, it's not just a ring, it turns out. It should actually be a simplicial graded ring, so in every degree, it is a different ring, and in fact, it's a different graded ring, and it's graded by a different group, or a different monoid. So in dimension 0, it should be graded by R. It should just be K of R. Dimension 1, similarly, it should be that. But in dimension 2, it should have a three-way grading. So it should be R to the cube graded, corresponding to the fact that I have, in the boundary of the two simplex, I have three different simplices, three different edges. And in general, at the nth stage, it should be R to the n choose 2 graded. And again, the way I've written here, dimension 0 is a slightly exceptional case. But in any case, the idea being to embed K of R plus into some bigger ring, which allows us to differentiate between different directions. In other words, the gradings are corresponding to the different directions. And so in this case, what you can see is that the tensor product operation actually works quite well. Over a ring like this, if you write it down, you can see that you can actually get a statement that says that the chain complex for, or I should say this module associated to the chain complex for the product is indeed the tensor product over a ring like this. So that's just algebraically. Then there's the filtration aspect of it, and you've got this ring will have two different filtrations on it. And so the question is going to be that when I take these tensor products, yes, I know I get the right thing at the end, but is it algebraically meaningful? What do I need to extract? How can I describe that E2 term based on this tensor product for this simplicial filtered ring? Okay. So again, this is something that is clearly very much at the early stages, but it looks kind of promising, and I think it would be actually fascinating if it worked out and one could see what the derived functors are that need to be computed in order to get at these metric spaces, the products of metric spaces with some metric. Okay, so I'll thank you for your attention then and take your questions.
Thank you very much for nice talk. Are there any?
See one over here.
Are there any questions, comments?
Just a very simple-minded, if I may.
Sure, sure.
So for at least a significant part of your talk, you
Yes.
assumed to be finite. I mean, your metric space is finite.
Yes.
What if you would go into infinite one but say bounded?
Bounded,
Yeah, because you
You
are.
know, yeah, it's interesting. I mean, of course, we could take any of the ordinary spaces that we deal with and just take all its points if we have a metric on it. And I think, yeah. So the question was, you know, throughout the talk, I dealt only with finite metric spaces, and the question is, what happens for maybe some infinite metric spaces, in particular bounded ones? And you know, the answer is that, of course, what tends to happen when you've got all the points in there, you tend to get the homology of X itself as appearing to be above dimension 0. And I think for something intermediate, well, we don't know. Well, I think there are certainly things that one could do, but of course the kind of induction that I'm talking about is not an option.
Okay, thank you. Any more
Yeah,
questions?
Wojtek.
Yeah, so you had these great examples of applications of trees, you know,
Yes.
the coming distance,
Yes.
this,
Yes.
evolution. Are there any natural applications of products of trees?
Well, you see, I think the thing is this, that what we want to try to understand ultimately are subspaces of L1 to some high n. Because it turns out the trees themselves can be embedded, in fact, as convex subspaces of L1 to some n. Okay. I think, you see, what we know right now is we just have these kind of hints of things that are showing up, this homology in higher degrees that are showing up for reasons that we don't understand, but they're indicative of this stuff with evolution. So the feeling is that if we can start to understand the subspaces of L1 to the end, maybe the convex ones as a starting point, then that would be, it would give us the insight to start to think or reason about what's going on. It's not clear to me that the products of trees are the most directly applicable one. It is one. But you know, part of the reason that that the trees occur in the first place is you've really got some very large L1, and now you start, you know, choosing, you know, certain particular mutations. And it's just a fact that because there are so many of them, that you're never going to have any overlap. I mean, it's that kind of thing. So if there are some correlations for things, for example, then you could have things like products popping up.
Okay, thank you. Any more? If not, please thank to the speaker again.